Hi everyone, Ewan here, and I hope you're all doing well today. This is part two of the isolating and solving different variables, and then we're just going through examples of common engineering, physics related equations that you probably will encounter in your studies. So if you don't remember, if you haven't seen part one, I would highly recommend it. So we just went over 5 examples: kinetic energy, rotational kinetic energy, energy of mechanical systems, Bernoulli's equation, Rydberg's equation, all these sorts of things. And you can find a link to this video in the description or in the comments. But anyway, today I have 5 extra examples, and as always you can pause the video and attempt them by yourself, but I'll just go right ahead and solve them. So the first one here, Van der Waals equation of state. This is all about molecular interactions in like gases and stuff like that. So this time we want to try and solve for P. So let's go ahead and so we're going to take away the brackets by multiplying v minus nb. We're going to put that to the right, so we're going to divide it. So that's going to give us p plus an squared over v squared, and this is going to be equal to nRT over v minus nb. And so you might be tempted to strike out the n's, but just remember that there's a minus sign here and they're not both multiplication, so you cannot do that. Anyway, next step, once that we have this, what we can do is simply put this term over here, we'll just pop it to the right, so just a minus. That will give us the final answer of P equals nRT over V minus NB minus an squared over V squared. Nice and easy for the first one. Here we go, and then let's hop on to the next one, second moment of area. So that's more for civil engineers. That's when you can use the second moment of area for any shape, for any kind of beam you have, to calculate the deflection, for example, under a load. So that's quite useful. But anyway, here we want to try and find D, which is the depth of the section in terms of dimensions. So let's go ahead, and that's going to be quite easy as well. We're just going to go a minus ay squared, which is equal to bd cubed over 12. And now we want to isolate d, so we're going to need to get rid of the 12 and the b, so we're going to multiply by 12 and divide by b, which is going to isolate d. So it's just going to be multiply by 12, so that's 12 over b, factor of I minus ay squared. This is equal to d cubed. And the final answer, d equals, so there's several ways of writing this, depends how you've learned it. So that's the cubic root, and we simply write the answer here. And of course the other way of doing it would have been to put everything in parentheses, and then just put power 1/3. So that is the same as a cubic root. There we go. Let's hop on to the next example. So it's this torsion. Same again, this is more for civil engineering actions under loads. So that's the twisting of a member on itself due to torque. And this one here, we want to try and find G. This is extremely easy. So if you've learned this in school, so basically when you have two fractions equal to each other, you can simply do some sort of cross. So G is equal to T times L divided by g multiplied by the angle. And this works for any other any letter that you want, so that will just give us g equals t times L divided by the angle multiplied by its coefficient. Now, if, as just a side note, this would work for anything. For example, if we were looking for L, then we would simply do like this. So we always multiply in the diagonal, and then we divide by whatever left. So if we were looking for L, for example, we would just go J multiply the angle, multiply the coefficient, divide by T. So there we go. So it's just a nice and easy way of doing it. And then if for any other reason you have, let's say, I don't know, or let's go for example trigonometry. If you have sine theta is equal to fx over 90, and then you think that this doesn't look the same as this because you don't have two fractions, but in fact sine theta is, you can imagine it as if it's over 1. So if you were looking for fx, for example, you would just go across, so 90 sine theta divided by 1, which is just 90 sine theta equals fx. Anyway, hopefully that was useful. If you're finding all the examples useful so far, I would appreciate it if you could just leave a like and subscribe. But here go for the other example, change in internal energy. So this is same again. I'm not quite sure what that is for precisely, but everything thermodynamics, heat transfers, that kind of thing. But for here we're looking for T1. So here again we're going to try and get rid of the brackets by getting rid of this term here and popping it on the left. So it's simply going to be a division of delta U over mcv is equal to T2 minus T1. And here we're looking for T1, so it's simply going to be T1, we're going to leave it on the right, so that's going to be T1 equals T2 minus delta U mcv. Fantastic, that's our final answer. And then next question, work done, polytropic process, same again, heat transfer, all that kind of thing. Physics, mechanical engineering. Here we're trying to find P1, which is over here. So same again, get rid of refraction. We can just multiply W, the work done, by n minus 1. So that's going to give us W n minus 1 is equal to P1 V1 minus P2 V2. And we're looking for P1. So we can get rid of this thing here, pop it on the left. So we just have to do plus. So that will give us W n minus 1 plus P2 V2 equals P1 V1. And last step, we're looking for P1, so we simply have to divide. We have to divide V1 to the other side. So it's just going to be W n minus 1 plus P2 V2 over V1. I hope you're not hearing all the wind and everything because it's a massive storm right now, as always in Scotland, to be honest. And that's equal to P1, final answer. There we go. So these are all the examples for today. I really hope that this was useful and if you learned something. If you have any questions about any of the things we've covered so far, then feel free to leave a comment and I'll try my best to answer it. But in any other case, hopefully you've enjoyed. If you'd please like and subscribe and maybe share it with your friends if you think it will be useful for them. But in any case, thank you for watching and I'll see you next time. Cheers.